All right, we're going to do some more things with vectors today. I'm going to skip the warm-up and jump straight into the new stuff. If you want to write this vector that's shown in component form, you actually did this yesterday, even if you didn't quite think about it like that. You found your horizontal and vertical components A and B independently at least. We're just going to make sure you write it as a vector in component form when you get all said and done. So if you're thinking about your horizontal component, A, draw this as a triangle and kind of label some things. Here's how I usually do these. So there's my horizontal component. My vertical component B would be right there. And then if you think trig functions, if you say that you want to find your horizontal component A, you could do adjacent, hypotenuse for your magnitude, and do cosine of that 65-degree angle, would equal A over 8. If you take cosine of 65 and multiply it times 8, you get approximately 3.381 for your horizontal component. If you kind of repeat the process for your vertical component, side B is opposite your direction angle, so you could do sine of your 65-degree angle, would have to equal B over 8, multiply by 8, and you'd end up with your vertical component B is approximately 7.250. Just to make sure you write it back in component form, horizontal component first, and then vertical component. Which, if you think about it geometrically, that kind of means that your coordinates of your point right here, your terminal point for your vector, are like 3.4 and 7.3. Which, if you look at it, makes sense for our situation, so you can kind of do a little bit of a double check for yourself. Vector in component form should look like that. Okay, this one's not in the coordinate plane, so we're going to have to treat it a little bit differently. We basically got two different amounts of force that are acting on some point. So maybe your point is like you've got a cup on a table and somebody's fighting, pushing it with force of 32 newtons one direction, force of 72 newtons another direction. You want to figure out how far it's going to travel. That would be your magnitude. So I'm going to go ahead and draw my two forces acting on my point right here. So let's say that you've got your force of 32 newtons acting on your point. So let's make this a magnitude of 32. I don't know the individual directions for these two forces, but I do know that the angle between my forces is 76 degrees. So I'm going to draw my second vector here. I'll try and sort of get it to scale. My magnitude on vector 2 is 48 newtons. And then my angle between those forces is 76 degrees. If I'm trying to find the magnitude of my resultant vector, remember your resultant vector is what you get if you add these two vectors together. So a lot of times when we did them like just individual additions, we just took like them and put them end to end. But for our situation here, it actually makes more sense to use that parallelogram rule and kind of turn this into a parallelogram and think about it that way. So if you think about it, let's get your resultant vector here by creating a parallelogram. I'm just doing some copying and pasting. So parallelogram can be created between your two vectors where their initial points are the same here. And then if you draw in your resultant, my resultant vector that I'm trying to find is this red line's magnitude right here. So that magnitude is what I am looking for. Okay, So if you use what you know about parallelograms, same side interior angles, or parallel lines if you think about it, same side interior angles should add up to 180 degrees. So it doesn't really matter which one of these two like triangles you're working with here. Let's say that I work with this one on top. I'm trying to find the length of the red vector, its magnitude. So I'm going to work with that purple triangle. I know that my same side interior angles should add up to 180 degrees. So if this whole angle up here is 76, then this angle down here in my purple triangle is going to be 104 degrees. I also know that parallelograms, opposite sides are congruent. So if I'm just focusing on this single triangle, that's going to be 32. Let me redraw it over here so that it's a little bit easier to look at just the information that we want. Okay, so we got 48, 32, angle between them is 104. We want this magnitude. We could use our law of cosines to figure out the length of that side in our triangle. So let's do that. So I'm going to call this x right here. I could do x squared equals 48 squared plus 32 squared minus 2 times 32 and 48 times cosine of our 104 degree angle. If you actually go through and do that and take the square root of the whole thing, you should get that that side in our triangle is 50.841. And that represents your magnitude of your vector. So magnitude of your resultant vector is 50.841 newtons. Other things you can do with vectors, you can add them like component-wise, your horizontal and vertical components. So instead of like getting a line segment as a result picture, you can get the component form. If you add like your two horizontal components together, get your new horizontal component, your two vertical components together, get your new vertical component. If you're scaling your vector up, like doubling it, you can multiply your horizontal and vertical components times that value. And if you're changing the direction, doing the vector going the opposite direction, you can change your components signs and you'll get the opposite vector. Let's do a few operations here. So say that these are your two vectors that you're working with, vectors A and B. If you want to add them and get the component result, you're just going to add the two horizontal components. So 6 plus negative 14. You're going to add the two vertical components, negative 3 plus 8. And you're going to end up with a resulting vector with a horizontal component of negative 8 and a vertical component of 5. If you're going to multiply vector A times negative 2, you're just going to multiply your horizontal component times negative 2 and your vertical component times negative 2. And your resulting vector is going to have twice the magnitude and opposite direction. So your resulting vector is going to be the vector negative 12, 6. You can combine some stuff, so you could do 5 times vector A minus 2 times vector B. So let's say you do 5 times vector A. You'd have 5 times 6 would get you 30, and 5 times negative 3 would get you negative 15. Vector B, you can either like multiply by negative 2 and just add them together, which I think is what I'm going to do, or you could multiply by positive 2 for vector B and then subtract them. I'm just going to take vector b times -2, and then add them together. So that'd give me, can't see vector b unless I zoom in here. That'd give me 28, and then -16. Add them together, you get a vector with a horizontal component of 58 and a vertical component of -31. There's also this operation called dot product that you can perform on vectors that lets you do some more physics applications. So dot product is calculated as if you take two vectors and multiply their horizontal components, multiply their vertical components, and then just add that together, you get this single number as a result. So you're going to get a scalar, just a single number as a result, not a vector. Sometimes people call this the inner product also. So if you want the dot product of vectors a and b, you're just going to be taking your two horizontal components, so 6 times -14, your two vertical components, multiplying them together, -3 times 8, and then you're going to add the results. So if you take 6 times -14, I am doing this in my calculator, you get -84, you get -24, and then if you add them together, you get a dot product of -108. You can use this dot product to find the angle between two vectors. So if you calculate, say you draw two vectors in the coordinate plane, u and v, and you want to calculate the measure of the angle between them, you can use the dot product to figure that out. It's basically just dot product of u times v over the magnitude of the two individual vectors multiplied together. I actually don't really use this formula. This is another, I just kind of turn it back into triangles and use what you already know. So I can show you both ways that you could do this here. So if you want to find the angle between these two vectors, a and b, let me go ahead and draw them in the coordinate plane here. We'll do it using the dot product first. So vector A is 6, -3. Oh man, I'm really terrible at making straight lines. So 6, -3 there for vector A, -14, 8 for vector B. Okay, I guess if I'm using the formula, I don't really need to draw them, but hey, there they are. So to calculate the angle between them, if you're using your formula, if you calculate your dot product of a times b, dot product of a times b is going to be equal to, we just did it, 6 times -14 plus -3 times 8. So that was our -108 for your dot product. And then if you find the magnitudes of your two individual vectors, so magnitude of vector b is, if you think little Pythagorean theorem here, or back to your formula for it, you could do 14 squared plus 8 squared and take the square root of it. Which is going to get you to square root 65. And then if you go to vector A and calculate its magnitude, you're going to have 6, -3, magnitude of vector A, 6 squared plus -3 squared. Take the square root. It's going to be square root of 45. Sorry, I'm not writing things down. It's 3 square root of 5. So if you plug them into your handy dandy formula, you know the cosine of the angle between these two vectors, so angle theta, we're going to call it, is just going to be negative 108 over our two magnitudes, 2 square root 65 times 3 square root 5. If you want to find the angle, you'd have to be doing some arc cosine. So you know that angle theta would be arc cosine of that value, which you could you could do it in 2 steps, type it in, and then use your answer key and do arc cosine of that value if you want to. Kind of depends on what you find easiest to type into your calculator. So if I do arc cosine of negative 108 over those two things multiplied together, I gotta type in my calculator. Then I got 176.82 degrees approximately. You can do this without using the dot product if you'd prefer, just by using what you already know about trig functions. So we want to figure out the angle between these two vectors. So like this distance. If you take it kind of one triangle at a time here, say right here, we start by finding that angle, which I'm just going to call angle A. I know that if I do like tangent of angle A, it's opposite over adjacent, so negative 3 over 6. So if you do arctangent of angle A, you get that it's approximately negative 26.57 degrees. So this angle right here if we're thinking about distance between these, so you don't really have to worry about direction of rotation. I'm just going to make that positive. If you go over here and figure out, let's call this angle B in this other triangle, you could do arctangent of negative 8 over 14, and you get that this is, well, you get the one in quadrant 4, which is like negative 29.7 degrees, but you're in quadrant 2, so you just come up instead of down by 29.744 degrees. So if you are wanting to figure out this angle so that I have my total, that angle is 180 minus your 29.744 degrees, which gets you 150.255 degrees. If you put those together, get the total angle between those two, so add them up. You also get the same value that we just got, 176.82 degrees. So it's totally up to you which way you prefer to do these.